Welcome, ladies and gentlemen, to the next lecture module. And this next lecture module is going to concern ion chromatography. And you know what? I know that you are super excited to learn about this piece of equipment. Or you have to watch the videos in order to do well in the class. So it's one of the two, but I hope that you just kind of click on these videos and find yourself enjoying some of the material that we're talking about, because it is a piece of equipment, and this piece of equipment you could be using in your future job when you start working in a laboratory somewhere. So as with all of the other chromatography sections, what we're going to do is we're going to break this down. And we're first going to start with the history of the instrument, tell you a little bit about it. How did it get its start? Who kind of came up with the idea? What was it first used for? And then we're going to talk a little bit about the theory. So how does this instrument actually work in the first place? And what are some of the things that I need to watch out for when I begin to use it? And then we'll talk a little bit about the instrument and all the pieces and parts that make it work. So if there's something that goes wrong, how can maybe I fix it? How can I replace it? How can I clean it? What's some of the maintenance that we can do on the instrument? And that's how we're going to end up with the lecture module in our troubleshooting category. All right. If you take a look at this cookie model, what you'll discover is that we did gas chromatography really the same way. So we went through a history of the instrument, a little bit of how it works, the pieces and parts, and then maybe how to do some maintenance on the instrument as well. All right, so that's all that I need to say about ion chromatography. Ion chromatography is abbreviated with a capital I and a capital C in a laboratory environment. And the IC can be hyphenated. And there could be some other things here on the end. And that is very similar to a GC that you probably have already learned a little bit about. So I could write GC-TCD, GC-FID, GC-MS, and that other abbreviation represents the type of detection that the instrument can do. And what we'll find out is that ion chromatography is really kind of beefing up its field. And we can get different types of detectors that we can put onto the ion chromatography systems. And those types of the detectors we'll talk about toward the end. But just keep that in mind. It is a hyphenated abbreviation. IC is the first half, and then the detection is going to be the second half. Okay, so let's get started. We want to know a little bit about ion chromatography and how this whole kind of field got started. And what I'm going to first start talking about is something called a zeolite. Z-E-O-L-I-T-E. All right, so if you've never heard of a zeolite before, what is the definition? Well, here's kind of the proper definition that comes along with it. It is a microporous alumino-silicate mineral. Oh my goodness, what does that actually mean? Micro means tiny, porous means holes. So basically, you think of this substance, and there's tiny little holes all in this substance. That's microporous. I would say think of a sponge, right? But sometimes a sponge will have really large holes in it, and that would not be microporous. So these, if you look at them under a microscope, or sometimes even with the naked human eye, you will be able to see some of these really tiny holes that are in this substance. Alumino, well, that's probably aluminum based, and silicate is probably silicon from the periodic table. And these two basically are coming together to form some type of rock. That's what it is, people. It's a little rock that has a bunch of tiny holes on the inside. So back in the day, there was a guy with the name of Axel. And his last name was Cronstedt. And what he decided to do is to take this rock and to heat it up in a flame, on a hot plate, whatever the case was. And what he began to see is that this particular type of substance generated quite a large amount of steam. And he's thinking, hey, okay, this steam is coming from water. And I'm heating the substance up, and this rock-like substance must be holding quite a bit of water, because when I heat it, that water is evaporating and it's turning into a vapor and it's leaving the object. So he believed that this extra water came from the rock. And this is how the word zeolite came into existence. Because the word zeo basically means to boil. And the word light means stone. Boiling stones. Ah, okay. So I can take these rocks in, and I can put them basically on a hot plate. I can heat them up, and they can liberate water for me. And that water, maybe I want to capture that water and do something with it. But they're kind of cages that house these water molecules. And we called them zeolites. And then upon chemical investigation and composition, we discovered that these stones were basically made up of aluminum and silica. That's kind of the two major players off the periodic chart that make this guy up. Now, there's other things involved too. Don't get me wrong. There's other things that are present inside of that rock. But they didn't quite know that at the time. All right, so if you want to take a look at a picture of a zeolite, I've got one for you. And here it is. So this is a zeolite. And as you can tell, this kind of granite-looking stuff maybe to you. This on the computer screen, you can easily see the holes, right? This one on top. And there's a penny there for reference to kind of show you what kind of size or scale this rock basically is. And then down here at the bottom, you maybe could see a little bit of more porous kind of stuff that's there. And they come to us in all forms and all sizes. But these were the types of materials that were basically brought into the lab during the time, heated up, and it liberated some water for Mr. Axel. All right, so this kind of began the whole idea and concept of ion chromatography. And you're probably wondering, well, what on earth does ion chromatography have anything to do with rocks? Well, further investigation showed that not just alumina and not just silica were involved in the structure of this rock. There were other things that were present. So the answer, or the question, is what other things were present that were there? What did they want to know more about? What caused this whole field of ion chromatography to kind of come into existence a little bit? Well, the story is that those other things, guess what? They were ions. So we need to talk about what a definition of an ion is. So, back to the drawing board. These things are filled with ions. All right, so what are ions? Well, hopefully in Chemistry 151 or 152, you learned what an ion is if you've completed those classes already. And an ion is a charged atom. Basically, what that means is that atoms typically want to be neutral. They don't want to be positive. They don't want to be negative. They want to have a zero charge. However, not all atoms or molecules are neutral. And there's an opportunity for an atom to lose an electron. And if it loses an electron, it loses a negative charge. And if this thing was neutral in the beginning, watch this. Let's say that this thing had 3 positives and 3 negatives. I just made that up. Who cares? And these things match. All right, well, if I go through and if I say this atom loses a negative, then all of a sudden we get a charged atom. And this charged atom, look, we've got 3 positives and we have 2 negatives. These two cancel out. These two cancel out. And what we're left with is a positive ion. So we can have atoms that carry with it a positive charge, and we can have atoms that are beginning to be neutral, that instead of losing, they gain an electron. All right, well, once again, if I start off with 3 positives and this atom has 3 negatives, I've just gained one. So I'll add another one on. Well, positive, negative, cancel, positive, negative, cancel, positive, negative, cancel. I've gained an extra negative, so therefore this thing is a negative charge. Well, 2 different variations of an ion can exist for this reason. What is that crazy atom going to be doing with the electron? Is it going to be kicking it out, or is it going to be taking it in? Meaning, are you the parents that are kicking your teenager out of the house because it's time for them to leave and grow up and be independent? Or are you the parent that's going to say, I feel sorry for all of those lazy kids that don't have a job and they're not picking up after themselves and they don't clean their room or make their bed, and I'm going to give them a home and I'm going to bring them into my house and take care of them? Well, if you kick them out and you get a positive charge, these things are called cations, and if you gain that electron and they become negative, these things are called anions. So cations and anions are really what we're dealing with. And that zeolite structure, that structure was a rock, and inside of that rock were pores, and I told you that when they heated this rock up, water was liberated. What they also discovered, though, is inside of these pores, there were cations. And these cations were things like calcium that carries a positive 2, magnesium, sodium, potassium, and those were the most common. All right, so sodium is a positive 1. Potassium is a positive 1. Magnesium is a positive 2. And if you go to the periodic chart, you could probably find an ion chart as well. And that will list all of the common positives and negatives that you might see that's out there in the field. And you can easily Google a ion chart if you're not really sure what I'm talking about. And you can find these all over the place. There's probably tables of these in a textbook for general chemistry. There's probably tables of these in a classroom or a laboratory setting, some form, some fashion, somewhere. But this is a typical ion chart that I keep referring to. So what you'll see is that the ion charts will typically be broken down into 2 sections. You'll see a cation side and an anion side. So the cations are all the positives. So look, we have things like ammonium and copper, lithium, potassium, silver, sodium, barium, calcium in the positive 2 section, copper, iron, lead, magnesium, nickel, strontium, tin, and zinc. And in the positive 3 section, we'll find aluminum and iron. And then we do have some that are positive 4, and that's lead and tin. Now, these are not all of them. These are just the most common ones that are out there that we might run across. But you're seeing that the typical positive charges are +1 through +4. You also had to probably use an ion chart to name compounds in a general chemistry class. So that was probably your first introduction to this type of chart when that happened. Over to the right-hand side, you'll see the anion section. And under the anion section, you see the same type of breakdown, -1s, -2s, -3s. It's basically relating to how many electrons they are gaining for the anion side, or how many electrons they are losing on the cation side. Under the -1s, you'll see acetate and bromide, chloride. We have this thing called dihydrogen phosphate, H2PO4. Fluoride, hydroxide, and then we have hydrogen carbonate, also known as bicarbonate, HCO3-, and then we have hydrogen sulfate, but that's also known as bisulfate, a new term and an old term, and that's HSO4. Kind of makes sense though, doesn't it? Hydrogen sulfate. Sulfate is SO4, and the hydrogen's in front, so we call it hydrogen sulfate. Hydrogen carbonate. Carbonate is CO3, and there's a H in front, so we call it hydrogen carbonate. We have something called hypochlorite, ClO-, iodide, nitrate, permanganate, and thiocyanate. Under the -2 species, we see things like carbonate, CO3, chromate, CrO4, dichromate, di means 2, so that's Cr2O7. Hydrogen phosphate, well, that's probably phosphate, PO4, with the hydrogen in front. Ding, 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 it is. Then we see things like oxide, which is just an O, an oxalate, which is C2O4, a sulfate, and a sulfite. One's SO4, one's SO3. And then finally a -3 charge, which is nitride, N, and phosphate, which is PO4. So these are some of the common cations and anions that you might run across in a general chemistry class or with our instrumentation course when we talk about ion chromatography. Basically what this is leading up to is that anything that's an ion, such as these on the table, can be measured and monitored using an ion chromatograph. Kind of makes sense, doesn't it? All right, well, what they found is that this zeolite had some cations in it. Out of the bunch of cations that's in existence, you saw some of them just now, calcium, magnesium, sodium, and potassium were typically the most common that they saw. And the reason is because these zeolites have to form. And they form basically where volcanic rock is going to be located, and ash. These two things are reacting with groundwater. And that groundwater is going to have some natural calcium, magnesium, sodium, and potassium that's coming along with it. So that's where all of these cation contaminants, if you want to think of it that way, gets embedded inside of the rocks when they begin to bring them into a laboratory and begin to look at the chemical analysis and the makeup of them. Well, we're going to fast forward a little bit, and now what happens is that we can make these. We can make them more uniform. And when we make them, if we make them uniform, we have more control over them. And the reason that we would want to make them is because actually now these things can be used as catalyst in a reaction. It makes it go faster. So for instance, Na2Al2Si3O10 2H2O. That is one structure of a zeolite. And I'm seeing my alumina and my silicate, basically, the Al2Si3O10. That is typically in every zeolite formation. And it looks like this one's carrying with it a little bit of sodium. Well, it's a hydrate. That's what the point or the dot 2H2O means. And anytime we talk about hydrates in a chemistry course, we talk about it having water associated with it. Water likes to hang out with the molecule. They're buddies. And that water molecule is going to come along for the ride because it's probably free and easy. All right, well, that water gets inside of the rock. We heat the rock up. We drive the water off. That's where it's coming from. We're not making any changes to the chemical structure. We're just getting rid of some of that moisture that the rock is carrying with it, and we're driving off that water in terms of a vapor. All right, so this is kind of the start of ion chromatography. And the reason I say that is because very early on, they were interested in how to get the cations out of the system. What can we do to clean this process up? We know calcium's maybe tagging along, or we know sodium is tagging along. So how can we get rid of it? How can we separate that out of the process? How can we clean up this substance and maybe do something else with that sodium or with that calcium because I don't want it behind for whatever reason that might be? So in the next video, we'll kind of continue on this track and this discussion about the zeolite and about the cation contamination that was found within it.